Hello, 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 CheersKevin here, and today we're jumping back into our kOS script designed to take a stock rocket from the launch pad to a safe landing on the moon. In the last video, we wrapped up a script that computed our burn time for a particular maneuver, and this was part of a larger function that could take the parameters for a maneuver node and safely execute it. And that's great, but our total script so far has a ways to go. Despite a lot of work, we really only have our initial ascent working. We still need to circularize our orbit, as well as sort out our transfer burn. Now, when it comes to circularizing, we could figure out how much delta V we need using math, and figure out a maneuver that way. But instead, I want to take a look at some of the magic that we can pull out of software, and let our program find the right maneuver all on its own. To do this, we're going to need two functions. The first one is going to be very simple. Its input will be a maneuver, and its output will be a score of how good or bad that maneuver is. If we give it a maneuver that crashes into Kerbin, we'll get back a bad score. If the maneuver would put us in a stable orbit, we'll get a better score. The second function is really cool, but a little different. This function will take in a maneuver, and its job is to give us back a better one. That is, one which will have a better score. What we can do then is take an initial bad maneuver, say a maneuver that doesn't do anything at all, and then improve it again, and again, until finally we have the best possible maneuver. But will this actually work? Well, there's only one way to find out. Okay, so it's actually been a little bit since I recorded that intro because, my sound booth is currently in pieces because we are finally in the new house, which is fantastic. It's resulted in a bunch of delays, but hopefully should mean that we're able to press on and get back to something close to a regular schedule. Close to that at least. Anyway, talked about in the intro the idea that we need two functions. And why do we need those two functions? Well, because we actually sort of jumped ahead a step. If we look at how our main function goes here, we do our launch, we do our ascent, we auto stage until we get to the apoapsis that we want, and then we shut down the engine. Then this execute maneuver thing, well, that's intended to help us circularize, but we're kind of missing a step because we need to actually figure out what the maneuver is first. There's sort of this implicit figure out how to circularize step that we just sort of glossed over because we were so worried about how do we actually execute a maneuver. Okay, so that's what we're tackling today with these two functions, the idea of improving a maneuver, and I'm going to call this circ. I'm going to call this, and we'll call the variable circ, and having a score for the circ maneuver. Okay, so these are the two functions that we need to create. We need to be able to, this thing should take in a maneuver and should give back a score of 5. Its score is 5. I don't know. This improve should give us back a maneuver and gives back another maneuver. So this one takes in a maneuver and gives us back a number. So those are these two functions. And how are we going to use these? Well, the output is what we'll eventually throw to. It should ideally be our perfect maneuver. So let me sort of pseudocode out what I have in mind here. We're going to say until score circ is the best it can be. And that's just a placeholder for now. Until it is the best that it can be, improve circ. And actually we'll probably say set circ to improve circ. Because this is going to be returning back a new maneuver, we want to set this maneuver to that. Now, of course, in this pseudocode, I'm kind of treating the description of a maneuver as though it's a single variable. We're only using this one name, when our execute maneuver actually expects 4 values. It expects a time, and then the delta V in the 3 directions that we can have delta V. So that's a little bit of a problem, but I actually want to be able to talk about my maneuver data as a single unit, because they kind of bundled together. If we're improving things, we're improving maybe one of the individual components, but it's still part of the total maneuver. So I'd actually like the maneuver to be a thing, some sort of unit that we can use. What I'm going to do is I'm going to say local circ is a list. And a list is a way to group some values in a list-like fashion. So I'm going to say, we'll steal that time seconds kind of demo code down here, and we'll say 0 delta V in the directions. And now this circ value is just going to be a list of 4 different numbers. And we can get these values out by saying circ index 0. That's going to give us time seconds plus 30 circ1 is going to give us 0, and then 0, 0, etc. As far as why we start with 0 instead of the first, 0 means the first element in the list. That's a quirk of programming, and you're just going to have to get used to it. Okay, so problem though is that here so we have this idea of we want to be able to score and improve this circularization list. And then we want to, ideally, that be represents our perfect maneuver, because we've improved it until it's the best it can be. We want to pass that into execute maneuver. Execute maneuver right now is just expecting these 4 values. So let me quickly refactor that off screen. And there we go. I've rewritten execute maneuver to just accept that circularization value, and now it only accepts 1 parameter, and then it'll just grab the individual values out when it's creating the maneuver node. So I've just decided, hey, there's an M list, a maneuver list, and it'll pull out the data and create a maneuver node from that. So now we can talk about these 4 values as though they're one thing, and that's going to be helpful. So what we'll do now is I'm going to actually comment out these lines because they're just sort of a description of what these 2 functions what their signatures are going to be. And we have this idea until score circ is the best it can be, which that's confusing. Set circ to an improved version of the circularization maneuver. So okay, that's fine. But how do we figure out that the score is the best that it can be? We need to replace this with some fake code that's a little more convincing. So what I'm gonna just start writing this out in a way that I know is kind of dumb, and then we'll see if we can actually improve it a little bit. So I'll say until false. So this is gonna loop forever, unless we say break, which is gonna break us out of this loop. Not a semicolon, but a period. So we can use that break to break out of this loop that otherwise will go on forever and ever and ever and ever and ever. Okay, so let's say local old score is score circ. And then we'll say set circ to improve circ. And now the next step is to figure out whether improve actually had an impact on the score. So let's see if we can figure that out. Well, let's think about, we'll compare the old score, say if it's less than score circ. We'll have an if condition and then an else condition, and then we'll figure out what to do in here. If the old score is less than the score of the new version, what does that mean? What are we considering a good score here? Is this like golf, where we're going to look for a low score? Or is this like most other things, where we're going to look for a high score? Well, in fact, what I want to do here is I want to suggest that golf is the easier thing for us to do, because otherwise we could have infinitely high scores. But what we can instead say is that our score value can give us back sort of a measurement of the error. And that's a little bit cleaner. So the perfect score is going to be 0. So if old score is less than the new score, which is the score of the new circularization maneuver, well, then we didn't make an improvement. And otherwise, we did make an improvement. So if we did make an improvement, well, then great. And let's continue trying to improve. If we didn't improve, then we want to break out of this loop, because clearly we've done as much improvement as we can, and we're kind of stuck. And in fact, we'll make this less than or equal to instead of just less than. And of course, since this else condition doesn't do anything, we can get rid of it. Now, this isn't great code, because if we score here and then we don't break out, then we go to the top here and we score it again, which means that if the score function takes a long time, then we're doing it more times than we need to do. And you could optimize this. You can make this a faster function. I will leave that as an exercise to you, because I don't particularly want to get into it. I mean, that seems meh. But this should work. What we're doing is we're saying, hey, score the current maneuver as it is, try to improve the maneuver, and then, hey, if we were able to improve it, keep going, see if we can improve it further. If we weren't, though, we're assuming we're as good as we're going to get, and then we can go ahead and execute the maneuver. So this is our top-level code. Now, you'll notice also that this is starting to get a little bit bulky for our main loop. What we ought to do is probably wrap this whole thing up into some sort of logical function as well, like circularize. We'll call it do circularization. And then we'll take all of this and extract it into its own little function called do circularization. And paste that all in here. So now this logic all about doing our circularization can exist in here. We've got this loop that's going to try and improve our circularization maneuver, and then we'll finally execute it when it's done. Now our main loop is a little more readable because we can see all the stuff that it's trying to do. But we've been going through all of this, and we haven't dealt with the two functions that we were supposed to actually write, right? There are two things in here that we really need to have. The idea of scoring a maneuver and the idea of improving a maneuver. So let's write those now. So I've written out the skeletons for these two functions. We've got the score function, which takes in a maneuver and gives us back. Actually, no, this is wrong. It doesn't take in a maneuver. It takes in a list of maneuvery values. So, okay, we've renamed these two data. And of course, I've had this little reminder that a lower score is a better score. So we can return 0. Say everything is perfect. This one needs to return something. Let's go ahead and just return the same value that we got. And this would complete our program. This thing ought to execute. So let's start with the score function because frankly, it's going to be a little bit easier. In this case, we're actually representing a maneuver node. We're representing it with these 4 values, the time and the 3 directions of delta V. And we're trying to figure out, hey, is this a good maneuver for us to execute? And what does that even mean? Well, we're trying to circularize. So our score function has to somehow represent whether something is a good circularization maneuver. How do we do that? Well, if we jump over to the kOS docs, we can get a little clue. So here I am on the maneuver node page. You've got all of this information. What I want to do is jump down to the maneuver node itself, the structure. And it says, hey, here are all of the suffixes. We've got delta V, burn vector, ETA, prograde, radial out, etc. And orbit. Oh, this is cool. The expected orbit after this maneuver. Now, orbit is a structure all of itself. So we can access this, and you can see by the hover text, maneuver node :orbit is the attribute. If we look at the orbit type, well, the orbit is a structure, and this is all on its own page. The orbit is a structure with a whole bunch of information we can look at as well. In particular, the eccentricity. What is orbital eccentricity? Well, we can click and find out. Aha! Thank you, Wikipedia. The orbital eccentricity is a parameter that determines the amount by which the orbit deviates from a perfect circle. A value of 0 is a circular orbit. Well, that sounds like a perfect circularization maneuver to me. Values between 0 and 1 form an elliptical orbit, 1 is a parabolic escape orbit, and greater than 1 is a hyperbola. All right, well, we don't particularly care about that. We just know that, hey, what we're aiming for is a value of 0. And this is why it actually helps that when we're setting up our score to target a low value is, well, we can just return the eccentricity of the orbit that we expect to happen if we run that particular maneuver. So if we're running a maneuver that circularizes as great, well, then our eccentricity of the new orbit should be 0. If we get something that's very lopsided, well, then it's going to be a higher value. So we're actually dealing with 2 separate structures here. We've got some maneuver, MNV. I'm just going to assume that we've added that somehow. And we're going to say maneuver orbit. And this is going to get us the predicted orbit after we've executed the maneuver. And then we're going to use another colon to get the eccentricity. And that's going to be our score. I'm going to say local score is this. Now, you might think that we could just return this value directly, but we can't. I'm going to show you why in just a moment. So, okay, actually, I'm going to show you why right now. What we need to do is somehow create this maneuver. And, well, we can do that. We already know how to do that because we can steal from our execute maneuver because there's a lot of code here that does exactly that. The local MNV is node. So, okay, yeah, let's copy and paste code here. Of course, in here, we're not using mlist, we're using data. So let's do that. And there we go. So we're going to take this data, we're going to create a maneuver out of it, but we need to add it to the flight plan. And in fact, I want to take a look at the docs to make sure that it says this, because it ought to. Aha, it does not, actually, but I happen to know from experience, unless this has changed, that you can't actually predict the orbit of a node unless it's been added to the flight plan, because KSP hasn't calculated what the predicted node is going to do, what the future orbit is going to be. So what we need to do here is add it to the flight plan. Oops. And then immediately remove it once we've taken our measurement. And that's why we can't just return things right here, because then we'd never get to this remove it line. So I'm going to say local score is the eccentricity. And remember, with a perfectly circular orbit, that should hopefully be a value of 0. Okay, so add maneuver and remove maneuver from flight plans. Well, we already have functions that do that. Add maneuver to flight plan. Ha! How about that? We've written usefully named functions, and we can just reuse them And that's nice and helpful. And yeah, remove maneuver from flight plan. Same thing here. We'll do that. And then instead of returning 0, we can simply return the score. Go ahead and save that away. And now this score function is all done. If we pass it data that represents the 4 values to create a maneuver, it's going to tell us what the eccentricity is going to be of the predicted orbit after that maneuver, which just so happens to be a great metric for, hey, is this going to circularize us or not? So cool, we're done with that one. Let's look at how to improve these 4 bits of data given what we know. So I said that score was going to be the easy one, but this is actually fairly straightforward as well. We have this list of these 4 values. Let's call them A, B, C, and D for simplicity's sake. And we need to return back a new list that is hopefully better. It doesn't have to be better, because that's in fact, in some cases, it's not going to be. That's the whole reason that we break out of this infinite loop. It has to, at some point, not improve, and that sort of makes sense, right? We can't have a better than perfect orbit, or better than perfect maneuver. So, what are the possible ways that we can modify this list to improve things? We know what we have sort of guaranteed. What we have sort of guaranteed is that we're not going to return something that's worse. So we need to hopefully return something better, and if not, we'll return something that's equal. So I'm actually going to keep this return data at the very bottom here. What I'm going to do is going to seem really dumb, and there are definitely cleaner ways to write this code, but effectively this isn't the worst thing. I'm going to say if score of a new list, let's just say data 1, data 0, data 1, data 2, data 3 is better than, or is less than, score to beat, which we've got to assign. Then return list data 1, or data 0, blah, blah. Then return this thing. And actually, if we look at what we're doing here, we're pulling out these individual values and then wrapping them up into a new list. We're not changing anything. Let's add 1 second to the time. So we're going to say, hey, let's create our score to beat. Let's say local score to beat is score data. Score the initial data, and then we'll try and see if we can come up with something better. So, score. This is, if this score is better than the score to beat, well then great, we found one. We found one that improves things. So we can just copy this and return it. Say, hey, I found something better. A better maneuver is the exact same maneuver that you gave me, but fired 1 second later than what you initially thought. So I could say, hey, what about just subtracting 1 second? So yeah, the exact same maneuver that you were going to fire, but 1 second earlier. So how about this? If score of incrementing 1 to the first value is better, then return that. If score of decrementing 1 to the first value is better, do that. And do this for all of the values. Here we try adding 1 to the second value. Here we try subtracting 1 for the second value. And this is a valid approach. It's ugly. It's a lot of if conditions, and it's a lot of words. But I mostly just copied and pasted, removed these, moved them around so that we've got these subtractions and these additions, and we don't even have to try things like +2, because we know that in our loop, when we do this improvement strategy, well, we improve it once. If maybe, let's say that we have the perfect orbit, but the perfect maneuver, but really the best thing would be to fire it 5 seconds later, well, then every time we improve, this +1 score is going to be a little bit better. It's not going to be perfect, but this +1 score will mean, hey, now we're evaluating the 4 seconds away from perfect, and then the next time it goes to try and improve it, it'll add a second, and it'll slowly climb its way to the best possible maneuver. There is a little bit of a bias here, and let me go through that with you. There's a little bit of a challenge. What if subtracting 1 down here is going to improve our score by a huge amount? Let's say we've got a crazy eccentric orbit, but if we just got that 1 bit of delta V off of here, we'd have a perfectly awesome score. And this is the way to do it, is just to remove 1 from this value. Well, we may never get to that, because maybe this is going to offer a very tiny marginal improvement. We've got a bias that we're going to walk in the direction that the first improvement that we find, not necessarily the best improvement that we find. So I'm going to clean this up a little bit. What I'm going to do is I'm going to create a list of lists. A list of lists. I'm going to say local candidates is a list. And I'm going to separate this down onto a bunch of lines. And I'll just copy and paste all of these potential lists. Okay, so now I have a list of all of the potential improvements that we think we might be able to make, and I've stripped out a lot of that long, messy code. I can actually zoom back in now because it's not quite as miserable as it was. There are still cleaner ways to do this, but this will work for our purposes. We're going to go ahead and also say local best candidate is data. And instead of returning data down here, I'm going to say return best candidate. Well, now that we have all of these potential candidates in a list, well, we can loop over that list. So we can say for candidate in candidates. And we can say, hey, if the score for the candidate is less than the score to beat, well, then set the score to beat to the score of the candidate. So now this is the new score to beat. And then set best candidate to the candidate. So we're going to check each of these things. We're going to say, hey, if you've got a better score, well, then you now have this. You're now the score to beat. So if this one says, hey, I found a slightly better one, but this is a massively better one, we're still going to end up getting there. And that's great. So we'll set the best candidate to candidate. Now, of course, if none of these are improvements, well, then this never is true. And so we end up returning the original value. One little tiny improvement that bothers me here is that we're calculating the candidate's score twice here. And if score happens to be slow, adding a maneuver, removing a maneuver, it could be a little bit of a pain. So I'm just going to create a variable. We'll say candidate score is score candidate. And then we'll just use that variable so we're not computing it twice. So if the candidate score is less than the score to beat, then the new score to beat is the candidate score. And then we'll set the best candidate to this candidate. Cool. Now our improvement function makes a little bit more sense. There are cleaner ways to do this whole list generation thing rather than copying and pasting all of this stuff here. But you know what? This will work for our purposes. And I think it's not necessarily easy to read, but you get the gist of what's going on. We're trying a step forward and a step backward on each of these individual values. Remember that we've got, and the first value is the time, the universal time, and then the delta V in the three directions. So, radial and prograde and normal. So we're saying, hey, radial normal plus 1, is that better? How about that? Is that better? We're trying all of the possibilities. This is called hill climbing, for the record. And let's see if it happens to work. Yeah, one quick thing to remember is that our do shutdown function at the very bottom here has a wait until false statement, which is generally useful. But that's not something we actually want in this case, because now we've added stuff after our do shutdown. So let's put this up in our main loop just so we don't screw up again, because we never got to our circularization function because shutdown was waiting forever. Let's try that. Let's jump over and see how we run. Oh no! Number of arguments did not match the number of declare parameters. Yeah, so when you have a function name called score, don't also create variables with the same name. This is trying to call itself. Even though we don't have parentheses there, it's trying to call itself, and that's a problem. We're going to call this result and return the result for our score function rather than assign it a value called score, because that's not smart. Okay, let's try that once more. All right, we're getting close. Is this the one? Oh, look at that. It is jittering something crazy. It's got a maneuver over there. It keeps adding it to the flight path to do some measurements and then removing it. And it is trying a couple of different things. You can see it is very stuttery because it's adding these to the flight paths, taking measurements, and then pulling it out. It's trying to find something eccentric. But how's it doing? It is slowly moving it further out. So it seems promising. This is going very slow though, because if you remember, we're only adding 1 second at a time, or 1 unit of delta V at a time. And it is trying to find a very circular orbit from that. So let's go ahead. Flight engineer is freaking out.
And I suppose we could add a weight statement so we could actually see how it's doing. But it is slowly pushing this out, trying to find a better maneuver. And actually, if you look at that, it's not doing too bad of a job in terms of every so often it flickers around. And we can see it does find a circularization. And it is getting that periapsis out there from what it's trying to predict. And it is figuring out that, hey, the best place to fire is probably at apoapsis. We didn't tell it that. And there we go. That is the maneuver that it found. It says it's going to be 451 meters per second of delta V. And it says this is going to be pretty darn circular. And I have to say that I agree. So that's a predicted apoapsis of 100. What is that, 100? Is that 100 or is that 106 or something? 100, yep, 199,920. That is pretty darn close. And we didn't have to tell it anything about how much delta V or any of this stuff. We simply told it the goal and told it how to make small steps toward a big improvement. And then we just sort of waited. And there we go. We are firing our maneuver as predicted. We have two steps. One is figuring out the good maneuver, and second is executing it. Let's see how we do. We get there, and then we cut off. Okay, no, we've got an error. Lock steering to maneuver burn vector. Ugh. Must attach node first. Uh-oh. Well, that's not good. Let's take a look. Well, of all the things, okay, so yeah, that's the issue, is that we locked the steering to maneuver burn vector. We didn't unlock the steering. Let's go ahead and just unlock the steering at the very end of things. Wow. And then we should be fine. Problem is, it was still trying to figure out how to steer at a maneuver that we'd removed from the flight plan. So, all right, fair enough. But the result is we still got everything done. In fact, if we look over at the rocket, we can see that it did print out it ran. So we already got through all of our steps. This is just some cleanup stuff that we forgot to do at the absolute very end of our script that left it firing and crashing and wonderful stuff like that. But we have got ourselves into a circular, well, it had been a pretty decently circular orbit. We've kind of maybe screwed that up a little bit at this point, but hey, that's what these things are for, right? Next up, we'll be looking at doing pretty much the same type of thing, but this time getting ourselves in orbit all the way to the moon. So I hope to see you in the next episode where we will tackle that particular problem. And in the meantime, have a great one. Cheers.